Okay, so let's talk about turbine induction systems. This will go pretty quick. There's not just a whole lot to it, aside from just making sure the airflow is guided correctly and it cools as needed. Turbine the one kind of key difference between a turbine engine and a recip engine is the sheer volume of air that a turbine engine tends to pull in versus a recip engine. A recip engine won't pull near the just displaced air that a turbine is, because ultimately a recip engine only has to like just replace just like a little bit of air to squeeze it down and fire it, whereas a turbine is constantly gulping in air, and the bigger the engine, the more air it gets. No one gets worried about getting sucked into a recip engine. Also, there's a propeller there that might have something to say about that. But the there have been more than one instances of people and things getting pulled into high bypass turbofan engines that got too close to the front. And so that's one thing you want to keep in mind with this, is just the sheer volume of air that these engines pull in. Okay, so let's just talk about the general theory of how everything is supposed to work, and we'll go from there.
Okay, so like we were just saying, that the turbofan engine, your turbo shaft engine, your turbo prop engine drinks a lot of air. That air gets ingested through the front, and it's used for two, potentially three things. First thing it's going to use is just to sustain combustion. That air has to get squeezed down so it can get banged in the back, and then turn around and produce the thrust that's needed to turn the turbines and keep the engine going. That's reason number one. The second thing that it does is it cools the engine off, and we're going to talk more about this as we kind of go through there. But essentially, all turbine engines are air cooled engines for the most part. The this air is going to go over the top of the engine. It's going to remove the heat, just in the same manner as a recip engine does. And then the last thing that it's going to do is going to be used to produce thrust. So if it's a turbo fan engine, the ducted fan is going to spin up, and it's going to grab that engine, and it's going to produce lift via on the blades, and then that's going to end up producing thrust on the back end of the engine. If it's a turbo prop, then the prop's going to do its thing. It's going to produce thrust just like any other prop would. The only time that the air is not directly being used to produce thrust is with turbojet engines, and then in that case, it's the thrust is a byproduct of the enhanced combustion that's happening in the engine. But that is the general theory. It's the air is always going to come in from the front, whereas like with exhaust, you might have the exhaust out the back, or it might be ducted up or whatever. The air on these are always going to come in from the front of the engine. Even in like certain helicopters, that have the engine that's kind of set back inside of a cowling and all this stuff, that air is still going to be ducted directly into the front of the engine, and it's going to work its way linearly down the shaft into the combustion chamber, and then out the back, and then it'll be channeled to wherever it needs to go from there. But that's the general theory of how a turbine induction system operates. It's really not. There's not that much to it. There's air out front. The engine's going to drink it. It's going to combust it. It's going to then use it for thrust, and it's going to use it to cool. Those are the three functions of those of that engine.
Let's talk about how the cowling can help shape the airflow into the engine.
All right, so the engine inlet of a turbine engine is designed to provide a relatively distortion-free flow of air in the required quantity to the inlet compressor. Now, sometimes they'll use inlet guide vanes. Sometimes they use the shape of the cowling to create the right amount of air at the right pressure at the right time. Now, the like we were talking about, the turbine engine just drinks air. It's much more than the reciprocating engine, and because of that, the air entrance passage is correspondingly larger. It's always going to be a lot bigger on a turbine engine than you'll get on a recip engine. So it's also critical in determining engine and aircraft performance, especially at high speeds. So this is going to become a bigger and bigger deal the faster and faster the aircraft goes. So Inefficiencies in the inlet duct results in a successively magnified losses through other components of the engine. So, like, let's talk about that. So, if you have, like, let's say a screw that's not fully seated in the engine induction cowl, whenever it's at ground speed, it's just taxiing around, and it really doesn't make a big difference, and no one tends to notice it or anything else like that, because after all, it's just a screw. But whenever you get up to altitude and the air is thinner and you're going a lot faster, the shock waves that screw is going to produce is going to disrupt the airflow going into that engine. And it's not going to be able to produce as much power. So even though it may seem nothing on the ground, at altitude, it can make a massive difference. And so there's a lot of care and engineering that goes into the design of these aircraft cowls. So as aircraft speed increases, thrust tends to decrease a little bit. So as the aircraft speed reaches a certain point, ram recovery compensates for the losses caused by increases in speed. So it means that the faster the airplane goes, the slower the air is actually being sucked into the engine, because whenever you're at ground speed and you're not moving at all, and you're at max thrust, that engine is drinking in the right amount of air that it needs to go. Now all of a sudden, whenever it's at max thrust and the aircraft is moving forward, then all of a sudden you have this reduction of how fast that air is relatively coming into the engine, and so therefore you get a slight decrease in pressure. Now, air pressure drop in the engine inlet is caused by the friction of the air along both sides of the duct and by the bends in the duct system. So smooth airflow depends upon keeping the amount of turbulence to a minimum as the air enters the duct, which is a lot harder than you would think whenever you start looking at the way that these ducts are constructed. On engines with low flow rates, turning airflow allows the engine nacelle to be smaller and have less drag. But on a turbofan engine, the duct has to have sufficiently straight sections to ensure smooth, even airflow because of the high amount of air that's just going through it. The choice of configuration of the entrance to the duct is dictated by the location of the engine within the aircraft and the airspeed and the altitude. And the attitude of which the aircraft is designed to operate. So the 737 is not really meant to do barrel rolls, but an F-18 is. And those engine inlets have to take into consideration the disruption of the air as the aircraft stalls or rolls over or pitches differently. To accomplish this, the inlet ducts are designed to function as diffusers with a divergent shape, decreasing the velocity and increasing the static pressure of the air passing through them. Meaning that whenever these guys design these inlet air ducts, they design it for a very specific purpose, so that way whenever the air comes in, it either is conducive to the straight flowing air, like a 737, or it will disrupt the air in such a way that it causes the right shock wave to hit at the right place at the right time to go into the engine at the right pressure. Now, the so what takeaway of this is that no one's going to ever expect you as a maintainer to know, like, the inlet total temperature equation or the inlet pressure recovery equation or anything else. But the point is that, like, this stuff has been engineered to a very, like, just into the minutia, and so you want to have an appreciation for that, so that whenever you're working on it, you always want to return it back to its certificated configuration, because that is the way that the engine is built to operate. If you start to deviate from that, you run a real chance of losing performance. And sometimes a little bit of performance can make a big difference in a certain phase of flight. So if the airplane is taking off, it's heavy and it's it's in a dirty configuration, and then all of a sudden you've done something that kind of disrupts. You don't think it's any big deal, but like you've done something that will disrupt the air going into the engine, and it causes it to slow down. You could compressor stall. You could just simply not generate enough lift, and then you could cause a crash. So you don't want to do that. Okay, the requirements of a high-speed single or twin-engine military aircraft in which the pilot sits low in the fuselage and close to the nose render it difficult to employ the older type single-entrance duct, which is not used on modern aircraft. They tried it on the X-30 or the F-32, and it didn't work. That's why it lost to the F-35. Some form of the divided duct, which takes air from either side of the fuselage, has become widely used. So for instance, the F-18 that you're looking at. This divided duct can either be in the wing root inlet or a scoop at each side of the fuselage. So either type of duct presents more problems with the aircraft designer than the single entrance duct because of the difficulty of obtaining sufficient air scoop area without imposing prohibitive amounts of drag. Internally, the problem is the same as that's encountered with the single engine duct: to construct a duct of reasonable length with as few bends as possible. Scopes at the sides of the fuselage are often used, and these side scoops are placed as far forward as possible to permit a gradual bend toward the compressor inlet, making the airflow characteristics approach those of a single entrance duct. A series of turning vanes is sometimes placed in the side scoop inlet to assist in straightening the incoming airflow and prevent turbulence. All right, so the so what is the F-18 you're looking at here has two engines that are set behind the pilot. All right, and there's a reason why it's behind the pilot, and the engine has to take in air that then has to go around the nose, the landing gear, all that good stuff. So in order to get the air in the cleanest state possible, they've put ducts up front to channel that air back. Now, what they were trying to do is try to make it as straight as possible with as little disruptions to it whatsoever. And keep in mind, you also have to account for the fact that the F-18 is going to roll, it's going to pitch up, it's going to pitch down, it's going to be flying upside down, it's going to do all kinds of stuff. And the entire time, you cannot disrupt that air going into the engine, because if you do, you create a compressor stall and you run the risk of blowing the engine up, crashing, and killing the pilot. So there's a lot that goes into these things, but that is a divided entrance duct example. You can see the same thing on like the OH-58, where the engine sits behind the pilot and they have to duct the air back. Then you'll have a largely straight but slightly curved duct going right back to the turbine. Okay, so there's another type. It's called a variable geometry duct. So the main function of the inlet duct is to furnish the proper amount of air to the engine inlet. So in typical, military aircraft using a turbojet or a low bypass turbofan, the maximum airflow requirements are such that the Mach number of the airflow directly ahead of the face of the engine is less than Mach 1. Airflow through the engine must be less than Mach 1 at all times. Once you get to the sound barrier, it starts disrupting things and bad things happen. So therefore, under all flight conditions, the velocity of the airflow as it enters the air inlet duct must be reduced through the duct before the airflow is ready to enter into the compressors. In other words, you need to create shock waves to slow everything down. So inlet ducts are designed to function as diffusers, decreasing the velocity and increasing the static pressure of the air throughout them. As with military supersonic aircraft, the diffuser progressively decreases the area in the downstream direction. Therefore, the supersonic inlet duct follows this general configuration until the velocity of the incoming air is reduced to Mach 1. The aft section of the duct then increases in area, since this part must act as a subsonic diffuser. In practice, inlet ducts for supersonic aircraft follows this general design only as much as practical, depending upon the design features of the aircraft. So, but for very high-speed aircraft, the inside area of the configuration of the duct is changed by a mechanical device as the speed of the aircraft increases or decreases. A duct of this type is usually known as a variable geometry inlet duct. That's what you see here. That it'll change based on where the air is at in the progression towards the compressor. A third method of this is to use a shock wave in the airstream. A shock wave is a thin region of discontinuity inflow of air or gas during which the speed, pressure, density, or air or gas undergo a sudden change. Stronger shock waves produce larger changes in the properties of the air or gas, and a shock wave is willfully set up in the supersonic flow of the air entering the duct by means of some restriction or small obstruction, which automatically protrudes into the duct at high flight Mach numbers. So think about like a VG, a vortex generator. It basically produces shock waves to maintain laminar flow, to push the air back on top of the wing and keep it from separating. This is kind of the same idea, but in this situation, you're trying to disrupt the air, because disrupted air slows down and increases the static pressure, decreases the pressure because you're decreasing the speed of it. All right, here's kind of what we're talking about. So essentially, you have supersonic air that's coming in here, but then when it hits the engine, it creates a shock wave and then slows the air down to allow for combustion to happen. Now, this is a big deal, and it's going to get bigger as time goes on, because we're at this point where supersonic flight is starting to become a conversation again. Well, one of the main challenges with supersonic flight is that beyond Mach 5, the air is so hot, but from just the friction of the engine passing through it, that it has to get cooled down before it enters into the engine for combustion. Well, there was a set of guys that had worked on this for a long time, like 30 some odd years, in a company called Reaction Engines, to build a supersonic intercooler. Now, if they were successful in creating this intercooler, they knew that they would be able to go beyond Mach 5, because we have other ways to mitigate the friction on the airframe itself, but the friction going into the engine was always the big challenge. That was the big limiting factor for supersonic flight. So these guys worked on it, and they eventually got it. Now, currently, Boeing owns what was left of Reaction Engines. It basically went bankrupt because this stuff is extremely expensive, and they never got a test flight off. But the technology is out there to create it, and so inside of your career, you could very well see passenger aircraft, or at least aircraft in general, going beyond Mach 5 for the first time in a sustainable, systemic way, to where it could actually be used by mankind. Okay, so it goes without saying the air also needs to be clean and free from debris. And so you'll see a wide variety of compressor inlet screens that is there to keep trash from coming into the engine. Depending on what environment the engine may operate in, you'll get different types of screens. So this is like off of I believe it's off of PT6, that's attached to a turboprop that's going to be flying around, up in the upper atmosphere. You generally don't have to worry about a whole lot of trash up there. Maybe the occasional bird on the climb out, but that's about it. Whereas if you are operating like an Allison 250 in a helicopter, you're going to have like K&N air filters that protect it, or particle separators is kind of the older technology that uses a vortex to separate the trash out of the air before it goes into the engine. But so what of it is that like your engines will always have some sort of screen or filtration technology that's attached to it to keep the engine clean as you fly around. There's also, you will have these little probes that in a lot of cowlings. They're not in all cowlings, but most of them will have some variety of this that's there to basically measure temperature and pressure that's coming in there. That will feed the ECU. It also feeds data to the pilot in some cases. Sometimes the aircraft won't report that kind of thing, but it definitely will in the ECU. That allows the ECU to understand, hey, look, this is the temperature on the outside. These are all the different things that we need to take into consideration, how we need to adjust the speeds and the different amount of fuel that's going to it, all that kind of thing. But just know that they're there. So if you're going to remove one of these cowlings, most of the time there's going to be at least a cannon plug or two to disconnect that will disconnect those probes.
All right, now we have air coming into the engine. How does it cool the rest of the engine?
Okay, so you can imagine that a turbine engine generates a lot of heat. Now, if only enough air were emitted to the engine to provide an ideal air-fuel ratio of 15 to 1, the internal temperatures would increase above 4,000. Basically, the engine would explode and burn up. So that's not really feasible, so we actually need more air for cooling purposes. So in practice, a large amount of air in excess of the ideal ratio is emitted to the engine to help cool it down. Now, secondary air, not the primary air that's going through the engine, but the secondary air that's passing over the engine, cools those combustion chamber liners down. The liners are constructed to induce a thin, fast-moving film of air over the inner and outer surfaces of the liner. Canannular type burners frequently are provided with a center tube to lead cooling air into the center of the burner and to promote high combustion efficiency and rapid dilution of the hot combustion gases, meaning they cool them off really, really fast. rapid dilution of the hot combustion gases while minimizing pressure losses. They don't want to lose pressure in there. They just need the cooling side of the air. They don't need to slow it down and drop the pressure. In all types of gas turbines, large amounts of relatively cool air join and mix with the burn gases after the burners to cool the hot gases just before they enter the turbines. So calibrated airflows are supplied to different zones of the engine to keep the temperatures around the engine levels that are acceptable. Keep in mind they don't want it to be too cool, but they also don't want it to be too hot either. So airflow provides for proper ventilation to help prevent buildup of any harmful vapors. Zone 1 is around the fan case that contains accessory case and electronic engine cooling, stuff like that. So that needs to be at certain temperatures. Electronics don't like to get hot. They also don't like to get super cold either, and these are going to operate in super cold environments. So that air has to be there. The heat, we need the heat, but we don't need too much of the heat. So if pressure exceeds a certain limit, a pressure relief door opens and relieves the pressure. So zone 2 is cooled by fan air from the upper part of the fan duct and exhausted at the lower back end of the fan airstream. And zone 3 is the area around the high pressure compressor to the turbine cages. So this zone also contains the fuel and oil lines and other accessories and things that we need to keep going. Air enters from the exhaust pre-cooler and other areas and is exhausted from the zone out the back end of the engine. But that's how we keep the turbine cool, is by the air that it's already grabbing and moving into for other purposes.
All right, let's talk about insulation blankets and shrouds. Insulation blankets are something that's kind of unique to turbine engines. There's nothing saying you're not going to find it elsewhere in the airframe or maybe even in some recip engines, but they are ubiquitous in turbine engines.
All right, so to reduce the temperature of the structure in the vicinity of the exhaust duct or thrust augmenter or afterburner, and to eliminate the possibility of fuel or oil coming into contact with the hot parts of the engine, it's sometimes necessary to provide insulation on the exhaust duct of the gas turbine engines. The exhaust duct surface temperature runs quite high. A typical insulation blanket and temperatures obtained at various locations are shown here. This blanket contains fiberglass as the low conductance material and aluminum foil as the radiation shield. The blanket is suitably covered so that it does not become oil soaked. Insulation blankets have been used rather extensively on many installations in which long exhaust is needed. Some auxiliary power units mounted in the tail cone of the transport aircraft that surrounds the exhaust tailpipe also provides cooling and protects the surrounding structure. I'll tell you, all over the commercial category aircraft, you'll find these insulation blankets. And the main thing to remember is to keep the blankets from touching anything, because they're supposed to insulate, but they're not fireproof, and they will burn through. And then also, whenever you go to pull them, look for FOD behind them.
All right, the big last one for engine air is bleed air. What is bleed air? Why do we use it? And what is I guess the so what behind bleed air for a maintainer?
So let's talk about bleed air. Bleed air effectively is a system that allows for compressor air to get pulled out of the compressor and then channeled to other parts of the airframe for different reasons. One of the things that is a primary function of bleed air is cabin pressurization and the heating and cooling of that air. The packs effectively need compressed and heated air to maintain cabin pressure and to maintain a cabin environment that you would actually want to be in. Another one is for pneumatic starting. So like you can do an electric start on one engine, and that one engine will provide enough bleed air to air start the APU and the other engine, or you can have the APU air start the other engines by simply closing a couple of valves and channeling that bleed air onto it. However, one of the primary functions of bleed air on a heavy commercial aircraft is de-icing. So let's talk about that in its own section.
Now we know from our previous studies that as we increase the velocity of air, temperature also goes down. As that temperature goes down, if there's any moisture out there, ice can form, and anti-ice systems exist to prevent that from happening. Let's talk about engine anti-ice and what we can expect from it as maintainers.
Okay, so one of the primary suppliers of heated air, or the primary supplier for heated air for anti-ice purposes throughout the wings and the rest of the aircraft, is the engine bleed air system, and you can see it here, like on the seventh stage bleed air of the LEAP engines. That's where you're getting a lot of your inlet anti-ice, and so for our purposes in this video, we're talking about the turbine engine anti-ice system. And so the engine anti-ice system is largely going to be built up around the inlet cowl, because the cowl is what will hang out there in the wind and uh, actually start collecting ice, because it's far enough away from the compressor section to not get just kind of organic heat, whereas you won't get heat inside of the engine because it's where all of the heat is actually being generated right there. So you won't see ice collect up around that. Where you will see ice collect up is on the inlet cowls. Like I said, because it's far away, but also because you're designing a apparatus to decrease air pressure, and as the pressure decreases, the temperature goes with it, and as it's going through the air, especially at altitude, decreasing the pressure even, or temperature even more. And if there's any moisture, ice is going to want to build up on that cowl, and then it's going to come off in chunks. It's going to go into the blades and then into the compressors, and it's just going to be this big drama fest of things that could totally preventable had you had your anti-ice system in place and working. And so that's the idea of anti-ice systems on the inlet cowl. Is they basically take bleed air, they heat through stainless steel tubes, and then they'll go up and route it through that inlet cowl and allow that air, that hot air, to just travel through there and then dump overboard, so that way it can warm that cowl up and keep that ice from forming. In the same way that you'll have bleed air going out into the wings and other parts of the aircraft that are prone to icing during icing conditions. Now, this is pretty common, and I would also tell you that a lot of aircraft fires start because of bleed air, because when this air comes out that's hot, it is very, very hot. And if you have a bleed air leak, that air is going to come out and it's effectively going to scorch whatever it touches. Now, sometimes whatever it touches is just a big, humongous chunk of metal that doesn't really seem to get bothered too much by the heat. Sometimes it's flammable and it catches on fire. So take bleed air leaks very, very serious, because they can start the fire and crash the airplane.